Hello, welcome to your Topics in Mathematics course. I am Mrs. Schofield and I am excited to lead you through this material, this whole course. It's going to be all kinds of different topics, starting with sets, then going into logic and truth tables, hitting some geometry, and then wrapping up with probability and statistics. So I think you will walk away with something that you can apply to your life. Alright, so let's jump right in and get started. We're going to start in Chapter 2 in the book, in your current book, the Survey of Mathematics with Applications. We now are in the 10th edition. Now, if your current book, if this is down the road and your current book has changed, don't fear, the content still is useful from these videos. But that's where we are right now, and sometimes I might be pulling up pages from the book and referring to it. Alright, so we're going to start in Chapter 2 with sets. We're going to look at set theory, definitions, and Venn diagrams. Starting with set concepts. What is a set? A set, in mathematical terms, is a collection of objects. These objects can also be called elements or members of the set. Your set can be anything. It can be, you're going to find that it's not always numbers in this course. So let's see, what can we possibly have? We could have, I want a pointer. I think I want a black pen. We could have a set of the cars that students in the class drive. That's one possibility. Why does that keep popping up there? A set of cars driven by students in the class. You could have something like that. That's one example. We could have a set of all even numbers. Of all even. So like 2, 4, 6, 8. Of all even, let's say positive integers, make it easier. So your set can be very mathematical, or it can be not mathematical. Like I was talking about, you could have a set of the cars driven by students in the class. You could have even positive integers. You could have something like the set of Mrs. Schofield's favorite books. So all of these, you can identify items that go in the set. And those each item would be called an element or a member of that set. So like the set of cars driven by students, an element might be a Chevy Malibu or a Toyota Tacoma, something like that. Set of all even positive integers, elements include 2, 4, 6, 8, 10, 12, etc. You can have a set of the best bed and breakfasts. A set of the best B&Bs in South Florida. Bed and breakfasts. So all kinds of things you can have in your sets. Now these collections can be well defined, meaning that the contents are very easy to identify. Let me switch color so that we can differentiate here. How about red? Well defined, you can definitely list what's in it. It's not that hard to sit there and come up with the items that should go in that set. So like the set of cars driven by students in the class, well, it's just a matter of listing what they are. So that's very well defined. We can definitely figure out what goes into that set, what those elements should be. The set of all positive even integers, yeah, we can figure out what goes in that set too. And no matter who writes out what that set is, it's going to be the same. So that's another example of a well-defined set. Set of Mrs. Schofield's favorite books. Well, just ask me, and I'll tell you what they are. So you can definitely figure out what those are going to be and put them into the set. Now the set of the best bed and breakfast in South Florida, that's questionable. That depends on people's opinions. So that is not well defined. You know, whatever I say may be different from what my husband says, which might be different from what the Travel Channel says. So we can't definitely figure out what should go in that set because it's personal opinion. So that's not so well defined. Alright. Now when we're trying to write about sets, you know, mathematics is a language, and when we're talking about sets, there's certain parts of this language that we have to use. So we're going to look at different ways to notate sets. And we're going to look at 3 ways to do this. The first one is description. You know, a set may be noted by a simple description of its contents. This method does not require symbols. Yeah, in description, you're just using words to basically talk about what the set's going to have in it. So, so with description, let's come up with the set. How about we'll just use words and say that we're going to talk about the set of even natural numbers that are greater than 0 and less than 20. Okay, let's say we're going to do that. So even natural numbers greater than 0 and less than 20. So all we had to do is just write words. Right there, that is description. What I just did, what I wrote down. Greater than 0, less than 20. And we know exactly what's supposed to be in there because of the way it was described with the words. Now if you want to actually list what goes in there, then you can use roster form. Roster form, you can list the elements if it's possible. And this method requires giving the set a name, and usually it's a capital letter of some sort. You can use whatever capital letter you want. I'm just going to use the capital letter P. No rhyme or reason. You use the capital letter, you say equals, and then you use these little braces to enclose the set, you know, to put that way people know everything inside of here is part of the set. And earlier with description I had said a set of even natural numbers that are greater than 0 and less than 20. So that includes 2, 4, 6, 8. I'm going to go ahead and list everything that's in that set. 10, 12, 14, 16, 18. It's a greater than 0 and less than 20, so I can't include 20. Less than doesn't include 20. So there you go. There's the set listed in roster form. Now if I want to talk about an element that's a part of that set, just a little note, this little symbol here looks kind of like a weird E, kind of reminds me like the E in Epcot or something, but it means element of. That's literally what it translates to. So if you use that symbol, you should see on the left some kind of elements from the set that you'll find on the right. So like in this case, if I want to use that symbol, I can say 6 is an element of, and then you list the set. You don't put set braces around the 6, you're just because you're listing something that was inside those set braces, inside the set. So 6 is an element of the set containing 2, 4, 6. I'm feeling lazy and don't want to write this whole thing, so I'm going to say dot dot dot. little ellipsis. Tells people, oh, keep going in that same pattern. And then I'll just go 16, 18 so that people know that it ends and where it ends. That's a little trick you're gonna see quite a bit of, a little ellipsis. If you have a pattern that continues a certain way, you can use those 3 dots to kind of be lazy and not write out the entire set. Just write enough at the beginning and enough at the end so that people know how it goes. If there is a pattern. If there's not a pattern, you might want to avoid using that ellipsis. But alright, so there's that symbol saying, oh, this item over here on the left is an element of this set over here on the right. And over here on the right should be a set. Now, one other way to notate a set is using set builder notation. Set builder notation usually takes on this form of some capital letter name equals, you'll notice the set braces, and you'll see a variable listed here in this bar. The little bar literally means such that. That's what that little bar means. Okay, so back to our set we just had. Let's use capital P again since we're dealing with the same set. We do have capital P is the set of the natural numbers greater than 0 and less than 20. Even natural numbers greater than 0 less than 20. So let's go ahead and do the same thing here. Let's let P equal, but with set builder notation we're going to say P equals all x such that I'm going to write x. So x stands in for all the elements. You know those elements we just wrote out earlier in roster form? 2, 4, 6, 8, 10, 12, 14, 16, 18. X is standing in for those instead of writing them all out. We're going to write such that x is an element of the natural numbers. This means x is an element of the natural numbers you have a little bit of flexibility in how you write the conditions, but here you're writing out all the requirements of the set. So another requirement of the set is that x is even. And finally, x has to fall between 0 and 20. And x is greater than 0 and less than 20. So you don't have to write out all these words. I was just putting that down there to translate so that you know what it means. But this right here, this is the set builder notation. This whole thing. That's the set builder notation. You have the little set braces, x, bar for such that x is element of natural numbers, x is even, and 0 is less than x, which is less than 20. So that's a different way of notating that set. Okay. Now, as we were going over those 3 ways to notate the sets, I was making references to some different sets, both one that I made up and also ones that already exist. The one that I made up is a finite set. You can definitely sit there and count up how many elements were in it. When you start listing the elements, there's an end to the list. You can list them and say, oh, like in the example here, set A has the lowercase letters A, B, C, D, E. So set A has 5 elements. I can definitely count a number for how many elements are there. In an infinite set, you can't count them all because there's so many. It's an infinite quantity. The elements just keep going on. An example is the natural numbers. We use the letter N, capital N, for natural numbers. So we've got the natural numbers 1, 2, 3, 4, 5, 6, and those keep going. They start with 1. They don't include fractions or decimals, and they keep going into infinity. But we can't sit here and list them all to infinity. That would take forever, and we would never be able to do it. So we use the ellipsis, the dot, dot, dot. And that says, oh, this continues in this pattern. And since there's nothing following the ellipsis, we know that it continues indefinitely that way. It doesn't end. So natural numbers are an example of an infinite set, and then like the set that we were just working with was an example of a finite set. The cardinal number for a set is the number of elements in that set. Let's say you have a set B, the cardinal number is denoted with a little lowercase n and then parentheses B, the name of the set. So let's say set B contains a star, a square. Remember, sets are collections of objects. They can contain all kinds of things. One of those @ symbols, an asterisk, a caret, and a pound sign. Some of you might recognize that as hashtag. Well, that's set B. I just listed it in roster form. It's a finite set, and it has 1, 2, 3, 4, 5, 6 elements. So the cardinal number of set B is 6. 6 is how many items are in that set. Earlier, the set we were working with, what was it, set P? Keep forgetting what I called it. Yeah, set P. It had those numbers 2 through 18. So set P had those numbers 2 through 18, even numbers. So the cardinal number of set P contains 2, 4, 6, 8, 10, 12, 14, 16, 18. Contains 9 numbers. So the cardinal number set P is 9. And that's it. So the cardinal number, if it's a finite set, you can count up how many elements, and then the cardinal number is how many there are. That's all it is. Now, if you're in a discussion and they say, well, here's your universal set, that's the big overall set that you're working with. From that universal set, you can have discussions. You can break it down into subsets, or you can start looking at different subsets and their relationships. And just a couple of things that you might encounter when you're doing this. Right now we're setting you up for all of your definitions. It is possible to have a set that has no elements. That's called the empty set or the null set. It's symbolized with either those empty brackets or with that 0 with the slash through it. I don't like writing zeros this way because to me this symbol actually means null set or empty set, which is a different concept than 0. The empty set or null set has a cardinal number of 0 because there's 0 items in it. Two sets are equivalent if they have the same cardinal numbers, but not necessarily the same elements. They can be placed in one-to-one correspondence. Two sets are equal if they have exactly the same elements and therefore also have the same cardinal numbers. Alright, let's see here. Let's say we have set A with the elements 1, 2, 3, 4, 5, 6. Let's say we have set B with the elements 2, 4, 6, 8, 10, 12. And let's say we have set C with the elements 4, 2, 1, 3, 6, 5. Okay. Now don't let set C freak you out. You can write the elements of a set in any order you want. It's okay. And then let's come up with set D. Say we have a set D that has 1, 3, 5, and 7. Okay, so set A, cardinal number of set A. Set A has 6 elements, so the cardinal number is 6. Cardinal number of set B. Set B has 2, 4, 6 elements. Cardinal number is 6. Set C. Cardinal number is also 6. Set D. Ooh, cardinal number is 4. Tricky, tricky. So we've got 3 sets with the same cardinal number and 1 set that was different. Now if they have the same cardinal number, then we can say they are equivalent. Sets A, B, and C are equivalent to each other. They have the same cardinal number. But only sets A and C are equal. So equivalent, they just have to have the same cardinal number, have the same number of items, but don't necessarily have to have the same items. Now they can, but it's not necessary as long as they have the same number of items. Equal though, in order for A and C to be equal, what this tells us is that they have all the same elements. And then D is not even in this because D has a different cardinal number and it does not have all the same elements of any of those sets. So it's not equivalent or equal to A, B, or Z. So there you go. So that's those definitions. Alright. Well, that wraps up some preliminary definitions. In our next recording, we're going to jump into taking sets and breaking them up into their subsets and looking at proper subsets and other definitions there. So please tune in again soon. I look forward to doing that with you.